So we had defined a tree as being a graph that was barely connected, meaning that between any two vertices there's only going to be one path that joins them. The tree will have no circuits anywhere, and if there's n vertices, there's going to be n minus 1 edges. We also looked at examples of a tree that would span. So a tree that spans must include all of the vertices of the original graph. So then we just kind of condense that and we call it a spanning tree. So a spanning tree is a tree that will be created from another graph. Now because we're actually going to pull out certain edges, now we were going to grab all the vertices because we want it to span. But because we're only going to pull out some of the edges and we're going to use another graph as a model for this, we sometimes call this a subgraph. So a spanning tree will be a subgraph from kind of this original graph that will contain all of the vertices of the graph, and it will have no circuits. Okay, so the idea is it satisfies the two criteria. So it spans and it's a tree. So we're going to be looking at some graphs and we're going to find some spanning trees. Now it says if a network has n vertices and m edges. Now network is just another word that would imply that you have a connected graph. Okay, so this idea for network, this is just going to be a connected graph. Okay, so if a network has n vertices and m edges, then m is greater than or equal to n minus 1. So in other words, the number of edges will always be greater than or equal to the number of vertices and then minus 1. Now, if the number of edges is exactly equal to the number of vertices minus 1, then the graph you're looking at, this network, will be a tree. If the number of edges is greater than the number of vertices minus 1, then the connected graph will have circuits. The redundancy of a connected graph is going to be given by doing the calculation of m minus n minus 1. Or in other words, it's the number of edges minus the number of vertices minus 1. Maybe another way to think about this is the number of vertices minus 1. This is going to be the bare minimum number of edges a tree has to have. Okay, this number of edges is the number of edges that are actually in your graph. The difference between the two of these will be how far away your graph is from being a tree. So, and we call that the redundancy. So if you were to do this calculation, if the redundancy is equal to 0, then that means you would have a tree. If the redundancy is greater than 0, then what this calculation will tell us is it tells us how many edges kind of quote-unquote past a tree we are. So we were going to have to then get rid of some of those edges then to make a tree using all those original vertices, which then we call a spanning tree. So let's see this in an example so we can kind of see what all these calculations are. Now it says for this graph shown, we're going to find two different spanning trees. Now for this graph, there is 1, 2, 3, 4, 5, 6, 7 vertices, which is going to be represented by the variable n. So n will be 7. In this graph, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges, which is represented by the variable m. For this graph, then, the redundancy, which is represented by the variable r, is computed by taking m minus n minus 1. So n minus 1, which would be 6, that would be how many edges a tree would have. This graph, however, has 11 edges. The difference between these two, 11 minus 6 is 5, is how far past a tree we are, which in other words, this is going to be how many edges we're going to have to remove in order to turn this original graph structure into a tree. So I'm going to record these spanning trees over off to the side. So I'm going to repeat kind of the vertice layout. Oh, that's E down here. Okay, so these are my original vertices. I want to connect these so that there are no circuits, but all of these will ultimately be connected to each other. And I'm going to do that with 6 edges. So out of this original structure, I'm going to delete 5 of the edges. So perhaps I connect A to E, E to B, B to F. So I have to do this along the original edges in the graph. I can't create new ones. So here's where I have these guys connected. Maybe I'll connect F to G using this way, G to C, and then C to D. I'll use that one. Cool. So this would be a spanning tree. I've used all of the original vertices of the graph, and these are connected and there are no circuits. Now I want you to notice that there is 1, 2, 3, 4, 5, 6 edges in this graph. I ended up deleting 5 edges. And the ones I ended up deleting in this particular spanning tree were this edge, this edge. Let's see here. I removed this one, the diagonal here, and the diagonal here. 1, 2, 3, 4, 5. Okay. So that's what this redundancy calculation tells us. It tells us how many edges we would have to delete to bring our graph to a state of kind of treeness. But we have to be very careful about what edges we remove because we still need this graph to be connected. So let's see a different spanning tree. So again, I'm going to have these vertices. So I have A, down here E, B, F, G, and then up here C and D. Let's take a look at a different spanning tree for this graph. Okay, so maybe from B, B has a lot of connections, so maybe I'll use that. B I can connect to A, to E, to F, to G, to C, and then I'm going to have to find some way to bring D back into the fold, so maybe I do the connection from G to D. Okay, that's just one possibility. Notice again I have 1, 2, 3, 4, 5, 6 edges in this tree. Okay, that's what this n minus 1 calculation right here is telling us. That is how many edges we need to be a tree. So then we look at the difference in these two to see how many edges I had to remove. And so here is an example of another spanning tree. And in this spanning tree, then I would delete a different set of 5 edges than from this first set. So I'm going to erase these just so we can kind of see what the original graph looks like. There is many, many other spanning trees other than just these two. Let's see a different graph where we go over this example kind of one more time. So we're going to find 2 different spanning trees for this graph. So again, I'm going to put down all the original vertices. Alright, and since I want 2 different spanning trees, I'm going to have another one, so I'll just go ahead and repeat all this right now. Alright, so I like to do those calculations before I get started, just so I know how many edges I'm looking at. So in this graph, I have 1, 2, 3, 4, 5, 6, 7, 8 vertices. That means in any spanning tree, there'll be 8 minus 1 or 7 edges. This initial graph has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 edges. So the redundancy of this graph is going to be 15 minus 8 minus 1, which is 7. So then 15 minus 7 is 8. So I'm going to end up in this original graph deleting 8 edges, because I only want 7 edges for this graph to be a tree, and I have 15. So I'm 8 kind of past my level of being a spanning tree. Okay, so this one sometimes is the magic number when I'm all said and done, because this is how many edges my ultimate spanning tree should have. So when I'm done doing this, I should have 7 edges in my graph. And I have to connect them along the original pathways. So let's see here. Maybe I connect A to B, A to D, A to F. Okay, so that's utilizing these 3 right here. We'll maybe connect D to G, D to E, and maybe I'll use E to grab these other 2 guys. Alright, so let's use 1, 2, 3, 4, 5, 6, 7 edges. So here is a possible spanning tree. Now something completely different, maybe over here. Alright, so I use these connections to kind of grab these middle guys. Maybe I'll use D to grab these outer ones right here, and I'll use E to grab these outer guys right here. So a completely different spanning tree, but again it uses 1, 2, 3, 4, 5, 6, 7 edges. Now again, in this graph there are many different spanning trees. These just happen to be 2 different examples. So notice for these spanning trees it still contains all of the vertices of the original graph, and there are no circuits. Now what we're going to start doing moving forward is we're going to say, okay, out of all of the different spanning trees that are possible, now all of these initial edges are going to have weights on them, so we're going to want to find a spanning tree that has the smallest weight. So that's what we're going to look at next.